Hello everyone, I'm Dr. Madi from Lisa Lab. I'm doing the postdoc research in the Lisa Lab. And we are going to do a very cool experiment today. Here is a rainy day. Me and one of our best Lisa researcher, Soonchunhyang, we are going to do the experiment and we are going to share it with you.
Hello, I'm Donghyun Ryu from Lisa Lab. I'm in master degree.
As you probably know, in the car there is a lot of ECUs, and ECUs are communicating through the CAN bus. And when they're communicating, this tiny computer, they make huge amount of data, and we are recording this amount of data by this laptop. They have a different method for collecting data, and also there is a different type of cans. So I'm going to ask our researcher, what is the different type of can? Can you explain it briefly what they are?
Okay, let's see what types in this car. In first one there is V can. In second one there is P can. Third one is C can.
Okay, so for example, C can is a stand for chassis can, right?
Yeah, it is.
So P can for the powertrain can, and they collect data from different part of car, right?
Yeah, it's true.
And can you please show us how you record data with this laptop? I heard that you have an application, right?
Yeah, it is.
What is the name of that application?
Its name is Can View. We already made it working. So let's see the first of this. First, activate this program. And you can see there was a lot of channels. For example, we will activate this first channel and set up a database entry code. It is bitrate 500 kilobit per second.
Great. So you give it a go?
Yeah.
Oh, great. So we are now collecting data based on different scenario, right? This is a data which car is generating during the when the car is this is a parking mode, right? Can we see when you drive how the data will change? I want to see if this is possible.
Okay, let's move on then.
Then okay, because we can have a different scenario, right?
Okay, let's see what will happen.
Okay. You saw some videos about how we are collecting data in Lisa, and this is a typical day. What we're doing, we are trying to collect data as much as we can. So as you can see here, there is a lot of facility. We call it test bed. So first of all, I would like to introduce yourself and tell us why we need these test beds.
Previously, you may heard about how we collect the data from multiple vehicles, and store it to this one big server. And from the one big server, we inject the data into the test beds to simulate the vehicle when data is collected. So by simulating data set, we can do so much things that we can do on real vehicle, like security testing that could be harm vehicle, or in order to test in safe environment, we need test beds.
So for the safety purposes. And may I know how many test beds we have?
Currently, we have so many test beds, 5 test beds for 5 different networks.
That's great. So you simulate a different kind of attack on the test bed, with no harming any driver, right?
During our test, no one hurts.
I saw these devices also. These are kind of test bed, or what? Can you please explain?
This is actually one of our test beds, the mini test bed we call it. So in here, it's an attacker and receiver and sender. So through here, we can not only work on the data set, we also work on the attacker side and defender side. Why we need this Jets Nano mini computer? We need to attack. It's used for attacker, AI-powered attacker, and also AI-powered defender.
So it is not rumor anymore. You are making something like an intelligent attack, at the same time intelligent defense. Very great job.
So it's like a field, a game field that attacker side attacks and defender side trying to defend it.
We have a real data here, and we have a, like as you said, meticulous process for injecting packet or mimicking different attack. Have you ever done any kind of simulation for the data here?
Yeah, of course. To us, collected data set is all on our shoulders. So we're not only focusing on the test beds, we're also considering about simulation. especially Victor's canoe simulation of Victor.
As I said, today is a very typical day in the LISA lab. Now we are having one of our best researchers. Actually, she is a lean expert, Miss Kim. I'm so proud to introduce her as one of our best researchers to you. So, Miss Kim, can you please explain for us?
Okay, hello, my name is Yoonji Kim. I'm master student. This is the test bed for analysis of lean and can relationship. Especially this very system is automated by programs because I want to show the result that lean and can data's relationship.
Wow, so this one is like this ultrasonic sensor, as you told me previously. I remember you mentioned that we have a 4 ultrasonic sensor like the car. You want to know when the lean data change, how it affect the can data, right?
Yeah.
Wow, that's great. And what was your ultimate finding in your research?
2 ideas analysis of lean-can relationship. First one is physical injection. Physical injection means obstacle installed here and moving. Moving automated. And then ultrasonic sensors have alarms, 3 steps. If obstacle is here, then the alarm sound like this. But if obstacle is close, the ultrasonic sensor, then it's like
this sound. Wow. So you like exactly you scale down the real model in this test bed, and you add this test bed to the existed can data set, test bed, right?
Yeah. And the second one is the Limpus.
Limpus.
Yes. Limpus, I inject the invalid data on the Limpus, then can data will change. So that alarm does not call. So I'm doing like this. Then I check the can and lean relationship simultaneously.
Very great. Yeah. I heard there is a very few research about lean and the can data's relationship and how they affect each other. Thank you so much for your time.
Okay, let me demonstrate my research. Here you can see 3 kinds of infotainment systems that I'm currently doing my research, and these are all different manufacturers, different kind of models. I explained that there is 2 kinds of methods for extracting artifacts, right? The first is the logical extraction. Here you can see on the left side that the current log of the device. Here you can see the all information of the device, like what kind of information is there and what kind of process are the driver doing. And you can even see the history of the connected devices. On the right side, you can see the current or executed processes, and you can even control the device through this terminal. There is a physical extraction method, right? And here is the different kind of infotainment systems PCB board. Right now, I am finding the flash memory of the PCB board so that I can do the chip off to extract the artifacts. And on the last, let me show you our laboratory's inventory of infotainment systems that we currently possess. There is many kind of infotainment systems here, from Hyundai and Honda. Yeah, okay, here is the end of my prepared demonstration. Thank you.
Established in our lab environment. So here we have 2 OBUs, and 2 OBUs have their own antennas for valid V2X communication. And here we have 1 LiDAR sensor. It's representing other ADAS sensors for automotive vehicles. And this sensor is connected with one of the OBUs. And here we have the RSU, which is the roadside unit. It's basically equipped alongside the traffic light controller on the road, and it enables V2X environment around its vicinity. With this testbed, we can experiment and prove our theoretical work of our project. Yeah, thank you.
This is a very typical day in LISA. We are not only work on the IVN, CAN data, lean data, we also work on the sensor data. We work on the LiDAR. This technology nowadays enable the vehicles to drive automatically. And now we have a very young and brilliant researcher who are working on the LiDAR, trying to detect the security vulnerability in the LiDAR. I'm very proud to introduce you Jung and Minchan, two of our best, youngest researcher. How it works, please? So now here, yeah.
This LiDAR sensor is here, and the wrapping paper, this one, and this one, and this one.
Okay, so the LiDAR sensor is here, right? This is the wrapping one.
Yes.
And when I move my hand, you analyze there, right?
Yeah.
Good. So we cannot reveal more because this is still this ongoing project, and they achieved one of the greatest award in Korea, right? Now we reached to this corner of lab, and we have one of our youngest, greatest researcher here, Mr. Josep. Yes. Yeah, I'm very happy to introduce him to you, and he's working on the 5G security. But before that, I mean, what is this room? Shield room, right? I know we are shielding against, cyber attack. Can you explain what this room is doing?
Yes, this shield room for blocking the signal like 4G and 5G, and we can make our own environment in that room. So
okay, can you take a look inside?
okay,
So now we see a lot of devices here, right?
yes,
Can you explain a little bit what devices are and what they do actually?
yes. You can see this one. This one is USRP that generating RF signal. This is for a 5G signal.
Great, great.
And this one is also for the little one is for 4G. So I can make our own device, our own environment in here. So over here there is so many mobile devices. So I can analyze each baseband or each mobile phone. So
Great, great. So currently, how many projects you are doing?
currently I'm making a 5G Open RAN environment now. So I'm making Open RAN environment for analyzing log. Analyzing
So
log.
yeah, you are like establishing ORAN.
Yes.
As far as I know, establishing ORAN is a big challenge. It has it's difficult, right?
Yes.
So when you set up your environment, then this environment will produce a log file, right?
Yes. Yes.
And later on, you can apply some technique for analyzing the log file, right?
Yes.
To know the security. Great, great. I heard that you are going to use the very advanced technique, process mining, right?
Yes. Yes.
Great. As I said, this is a typical day in LISA, and now we are going to this lab. But before everything, I want to introduce one guy here, Prof. Yim. Yes, he's always watching this researcher. Hello, Han, how are you?
Oh, I'm fine.
Yeah, look, wow, great, great. We have a good researcher like him. He's always busy and do the things. So I want to go to that corner, very quiet corner. But before that, look at the Yejin is here. Hello, how are you? Great, what are you doing?
I'm making presentation for IDX education PPT.
Wow, wow. Look at this cozy place. We call him Mrs. Blue. Ooh, everything is great. Okay, take care.
Yeah.
Bye. So, as I said, we are going to that really quiet corner. So, as we mentioned in the previous presentation, we are collecting data from the car, test bed, and all data ended here. For these two researchers, it's a big job to analyze data. Mr. Kamarol and one of our PhD student, Reza. As I said, in this quiet corner, our team analyzes the data which collected during all this experiment. So, Reza, can you please tell us?
Thank you, Dr. Mahadi. At first, our data collection team collect the data set. So that raw data we collected from them and clean up with our own format, and they collect several types of data set from different cars, for electronic car, from mechanical car, and their structure inside structure is very different, and their data pattern also different. So those pattern we have to recognize from our normal. We call it feature extraction. Then on those car we collect different types of attack data set like DOS, fuzz, replay, malfunction, and different types of stealthy type of attack data set. So after that we compare those attack data set with normal data set, and after that we extract the feature, and in CAN there is a several types of data set. So which feature is the responsible for which operation or which abnormal behave, we try to find out this. According to this we label the data. So after labeling the data we put into the deep learning model, and we try to find out which model, which architecture is the best for IDS, and after that we compare for the hardware configuration, which hardware configuration is the best, computationally based,
Yeah,
or
great.
low cost.
Yeah, great. You are continuing our typical day in Lisa, as I said, and I'm so happy to introduce one of our bright youngest researcher, Mr. Ibrahim, who is working on this safety system. As you saw in all of the previous presentation, we mostly focus on the security, and the cybersecurity of car is a concern about safety. So here in Lisa, we embark on the safety system for the car as well. So Ibrahim, can you please introduce yourself to us and tell us what you are going to do in your research?
Thank you, Dr. Mahdi. As you know, millions of traffic accidents happen yearly, and you can see a lot of people dying on these traffic accidents. That's why after 2014, government started focusing on preventing these kind of accidents by analyzing the emotions of drivers, because traffic accidents are closely related to emotions, both positive and negative. You can see a lot of types of research done in this field, like voice recognition, electroencephalogram, electrocardiogram, but the most widely used technique for emotion recognition nowadays is facial expression recognition, because you can see a really great boost in AI systems, in AI technology. And CNN, convolutional neural networks, achieved great results in defining the emotional state of the drivers. And actually, I started my research. I started this research approximately 7 months ago. And when I started using vanilla CNN models, I discovered some problems, because they are too high in computational power and low in test accuracy, lower than 90%, which is not good if we want to implement them in the intelligent vehicles. So what I decided to do, I decided to optimize those CNN models and boost the accuracy of the CNN models and decrease the computational power.
Wow, that's great. Yeah.
So we came up with a new technique, which is called patch extraction attention layers. I changed the structure of existing frequently used and famous CNN models like ResNet50, Inception V3, Exception, MobileNet V1, and other and 5 more models. And I changed the structure. I boosted the accuracy by at least 8%, at most 10%, and I decreased the computational power of those models by tenfold on average.